Talking through the solution to question 3 from the 2015 exam paper for Maths Graphics and Virtual Environments. So you're told you have a three-dimensional virtual environment which consists of an aeroplane, and the centre of the aeroplane is at point C, given by this 3 tuple, and current position or current direction, but it's pointing in, is given by vector D. And what we want to do is calculate a roll rotation of pi over 4 radians. Okay, so roll means it's going to rotate about this vector D, pi over 4. Okay, a 4 by 4 matrix R, which combines several different transformations to achieve this roll, is given here. Okay, so R is given by these 7 matrices multiplied by together. Well, actually, there are just 4 matrices, 3 of them are inverted. So you have the T, Rx, Ry, and Rz. Question asks, why are 4 by 4 matrices used? Well, quite simply, if we use homogeneous coordinates for positions at points, then we can apply translation. Okay, so rotation and scaling does not require homogeneous coordinates, but translation does. So that's why we use 4 by 4 matrices. Explain the roles of the matrices T, Rx, Ry, and Rz. Okay, so T is translation. So the first thing we need to do is move the aeroplane, but so our vector C, our position C here is at the origin. Okay, so C was given by 1, minus 2, and 3. So if we translate by minus C using this translation matrix here. So translation matrix is the identity matrix with the final column consisting of how much you want to move in the X, Y, and Z direction. Okay. Rx, Ry, and Rz are rotation, and what we want to achieve is we want D to be rotated so it points along the Z axis. Okay, assuming a left-hand coordinate system. These are the rotation matrices which you're expected to be able to remember. Okay, the first thing we need to do is rotate D about the y-axis. So here we've got a diagram. If we're looking down the y-axis, and remember the y-axis points vertically upwards. Okay, let's say D is pointing in this direction, and we want to rotate it so that D points along the z-axis. Okay, so we want to rotate it by this angle theta. We know what dx and dz are. Okay, so therefore we can calculate what cos theta and sin theta are. The reason we need cos theta and sin theta is because those are the elements of the Ry matrix. Okay, so cos theta is adjacent side, which is dz, divided by hypotenuse. Now the hypotenuse, okay, we're assuming we're only in the xz plane, so dy would be 0, so the magnitude of d would be dx squared plus dz squared, which in this case is 13. And sine theta is opposite, which is dx, in our case is 2 over root 13. Okay, so if we substitute those two quantities into our Ry matrix, we get the rotation matrix around the y direction. Okay, now assuming that's been applied to D to give us D dash, okay, we now need to rotate around the x direction so that D dash is pointing along the z-axis. Okay, so let's assume that D dash is pointing upwards, so dy is positive. We need to rotate clockwise, okay, around the x direction so that D dash is now pointing along z. Okay, so the adjacent side this time is square root of dx squared plus dz squared, which was our length here. Okay, and the opposite side is dy. Okay, so using the same as before, cos theta is adjacent over hypotenuse, so in our case it's root 13 over root 14, and sine theta is dy over the magnitude of our vector d, this time including all 3 components. Since in this case dy is positive, we've had to rotate clockwise. If dy was pointing down here, we'd have to rotate anti-clockwise. So essentially, this means that all of these vectors here, all of these rotation matrices here assume an anti-clockwise rotation. So if we change the sign of sine from bottom left here to top right, so that's bottom left assumes anti-clockwise. If we put that negative there, it assumes a clockwise. Okay, so that's why that's a negative there. Okay, so this gives us our rotation vector around the x direction. And finally, to perform the roll, we simply substitute in pi over 4 into the rotation matrix for Rz. Okay. Now pi over 4, cos and sine are both equal to 1 over root 2, or if you prefer, root 2 over 2.